Picture a machine that could take you apart, scan every particle of what you are, and rebuild you perfectly on a world light years away. Everyone who steps off the other side is smiling. Everyone swears they felt nothing, that they simply blinked and arrived somewhere new. But here is the thought that finds me in the dark. The person who walks in has to be taken apart for the copy to be built. So is the one who opens their eyes across the galaxy really you, carried safely over the void, or a flawless stranger who has inherited your entire life, while the real you quietly ended on the pad and never knew it? For 40 years, a single law of physics has had a chilling answer about whether a second you could ever exist at all. And a few months ago, 2 physicists found a way around it. So let me ask you the question that will not let me sleep. If you can be copied, are you still the only one of you? Get comfortable and settle in. Subscribe if you have not already, and stay with us tonight, because the answer runs all the way down to what the universe will and will not ever allow a person to be. Let's get into it. Part 1. The question that keeps me up at night. There is a question that finds me late at night, usually when the house has gone quiet and there is nothing left to distract me from it. The question is this: if you stepped into a machine that could take you apart, send the information about every particle in your body across space, and rebuild you perfectly somewhere far away, would the person who stepped out the other side still be you? Or would that person only think they were you, while the real you, the one who walked in, quietly stopped existing on the pad? I know it sounds like the kind of thing you're supposed to shrug off and file away with the other unanswerable puzzles, but the strange thing is that this is not only a question for philosophers or for late-night wandering minds. It turns out to be a question about physics, and physics, for the last 40 years or so, has had a very specific and very unsettling answer. Most of us first met the idea of teleportation through a television show. You have almost certainly seen it, even if you have never watched a single full episode. A crew stands on a softly lit platform, someone reaches for a control, and the people on the platform dissolve into a shimmer of light and simply vanish, only to reappear moments later on the surface of some distant world. It looks effortless. It looks clean. Nobody on the show ever seems worried about it, and that is exactly the part that has always bothered me. Because when you actually stop and think about what a machine like that would have to do, there are really only 2 ways it could possibly work, and neither of them is as comfortable as the show makes it look. Here is the first way. The machine could take the person and somehow move them, particle by particle, physical piece by physical piece, carrying the actual material of their body from one place to another and setting it down again in the same arrangement. In that version, the thing that arrives is made of the same stuff that left. It is genuinely the same person, transported. That feels reassuring until you realize how absurd it is to physically ferry every atom of a human being across light years of space in the blink of an eye. So most people who think about this seriously assume the machine must work the second way instead. In the second version, the machine does not move you at all. It scans you. It reads out the complete blueprint of what you are, every particle, every connection, every tiny detail, and it transmits that blueprint as pure information. Then, at the far end, a second machine takes that information and builds a fresh body from new material, atom for atom identical to the one that was scanned. And here is the part they never show you on television. In that second version, the original almost certainly has to be destroyed. The scanning either takes you apart in the process, or the machine deliberately dismantles what is left once the copy is safely made, because otherwise you would have 2. Sit with that for a moment, because it is the whole knot of the thing. If the teleporter is really a scanner and a builder, then the person who arrives on the alien world is a copy. A perfect copy, yes. A copy that remembers walking onto the pad, that has your memories, your habits, the little scar on your knee, the song stuck in your head. That copy will feel, with total conviction, that it is you, that it simply blinked and arrived somewhere new. But the you that actually walked onto that platform, the continuous thread of experience that was reading these words a moment before stepping on, that thread may have ended right there. 2 ways to read the same event. In one reading, teleportation is a miracle of travel. In the other, it is a very sophisticated way of dying, over and over, and being replaced each time by someone who cannot tell the difference. And the truly maddening thing is that from the outside, from the point of view of everyone watching, The two readings look absolutely identical. There is no test you could run afterward to tell them apart. The copy passes every check. The copy is, by every measurable standard, you. Now imagine you are the one standing on the platform deciding whether to step forward. Picture it as vividly as you can. The room hums with a low, steady sound, almost like a held breath. Beneath your feet, the surface of the pad is faintly warm, and a soft light rises around you from somewhere below. Somewhere across an unthinkable distance, a receiving chamber waits, empty, ready to assemble a person out of nothing but a stream of arriving information. You're told it is safe. You're told thousands of people do this every day and step off smiling on the other side, and every one of them will tell you it worked, that they felt nothing, that they are perfectly themselves. And still, in the half-second before the light takes you, a small and ancient part of your mind whispers the question that no one on the crew ever asks out loud. Will it be me who opens my eyes over there? Or will it be someone who's about to inherit my entire life, while I end here, in this warm and humming room, and never know it? You will never get to hear the answer, because whichever way it goes, the person who finds out will be the one standing in the other chamber, and they will be certain, absolutely certain, that nothing was lost at all. For a long time I assumed this was just a fun problem to turn over, the sort of thing with no real resolution, a puzzle you could argue about forever without anyone ever being right. What I did not know, for years, was that the deepest layer of the question is not philosophical at all. It is written into the laws of nature. There is a rule in quantum physics, a rule so fundamental and so quietly powerful that it took physicists decades even to notice they needed to write it down, and that rule has something very direct to say about whether a perfect copy of you could ever exist. It is called the no-cloning theorem, and once you understand it, the teleporter question stops being a fantasy and starts being a genuine consequence of the way reality is built. Because everything, when you go far enough down, is made of quantum information. The particles in your body, the arrangement of every atom, the pattern that makes you specifically you rather than anyone else, all of it is, at bottom, quantum information. And the no-cloning theorem is a statement about exactly that. It is a statement about whether quantum information can be copied. The answer it gives, the answer physicists have believed for around 40 years, is startling in its bluntness. It says no. It says that you cannot make a perfect, independent copy of an unknown quantum state. Not because our machines are too crude, not because we have not been clever enough yet, but because the mathematics of quantum mechanics forbids it outright. And if that is true, then it means something almost too strange to say plainly. It means that you, the specific quantum pattern that you are, cannot be copied. There can only ever be one of you, not one at a time for now, until technology catches up. One, full stop, guaranteed by a law of nature, the same way nothing can be pushed past the speed of light. The universe, at its most basic level, seems to have built in a rule that protects your uniqueness so thoroughly that no machine, no matter how advanced, could ever produce a second readable copy of you and set it walking around. It is worth noticing how strange our comfort with copying really is, because it is exactly what makes the teleporter question so slippery. Every day you send messages that are duplicated a dozen times between your hand and someone else's screen, and not once does it occur to you to mourn the original text, or to wonder whether the words that arrived are the same words that left. Of course they are the same, you would say. They are just information, and information is the kind of thing that can be in many places at once, without any of the copies being less real than the others. We have built an entire civilization on that intuition, and it works flawlessly, right up until the moment you try to apply it to a person. Because if you are only information, then perhaps you are like the message, freely copyable, and the person on the far side of the teleporter is simply another perfect instance, no more and no less you than the words on a friend's screen are the words you typed. But if there is something about you that is not like ordinary information, something that cannot be freely duplicated, then the whole comforting picture falls apart, and the person who steps off the pad becomes a genuine mystery. This is not a new worry, even if the physics is new. Human beings have been circling this question for thousands of years, long before anyone had heard of a qubit. The old philosophers asked whether a ship whose planks are replaced one by one, until none of the original wood remains, is still the same ship. They asked whether you can step into the same river twice, when the water you touched a moment ago has already flowed downstream and been replaced by new water. What all of these puzzles are really asking is what it is that makes a thing continue to be itself over time, when its parts, its material, its very substance are always changing. And for all those centuries, the question stayed safely in the realm of philosophy, the kind of thing you could argue about pleasantly without any risk of an answer. What has changed, and changed only recently, is that physics has walked into the room and started making concrete, testable statements about it. The question of whether you can be copied is no longer only a matter of opinion. It has become, in part, a matter of law, the law of quantum mechanics, and that law has a great deal to say. I want you to hold on to that phrase, because we are going to come back to it many times tonight, and each time it will mean something a little different. Only one clear copy. That is the promise the universe appears to make. Only one clear copy of the pattern that is you, ever, anywhere. For decades that promise seemed absolute, a locked door with no keyhole, one of the few things in all of physics you could lean on without worry. And then, very recently, two physicists found something that made the whole field stop and look again. They found a way to make copies after all, real copies, perfect ones, and they showed it working, not just on paper, but on an actual quantum machine. The headline said they had shattered the most unbreakable law in quantum physics, that the rule protecting your singularity had finally cracked. What they actually found is stranger and more beautiful than a broken law, and by the end of tonight you will understand exactly what it does and does not mean for that person standing on the teleporter pad. But to get there, we have to start with the rule itself. We have to understand why, for 40 years, the universe has apparently insisted that there can only ever be one of you. Part 2. The rule that forbids a second you. The rule we're talking about arrived surprisingly late to the story of quantum physics, and that fact alone tells you something about how sneaky it is. Quantum mechanics, as a working theory, was already essentially complete by the end of the 1920s. Physicists had the equations. They could predict the behavior of atoms, the colors of light, the way particles dance through their strange probabilistic world. For more than 50 years after that, thousands of brilliant people worked with these tools every single day. And in all that time, nobody wrote down the simple, devastating fact that you cannot copy an unknown quantum state. It was hiding in plain sight, folded into the mathematics they used constantly, and it took until the early 1980s for anyone to actually state it clearly. When they did, in 1982, it came from a physicist named William Wouters, working with Wojciech Zurek, and independently from a physicist named Dennis Deeks in the same year. They gave it a name that sounds almost too plain for what it does. They called it the no-cloning theorem. Here is the thing that makes it feel so counterintuitive. In the ordinary world, the world you and I live in, copying is the easiest thing imaginable. You copy a document by pressing a button. You copy a photograph, a song, a file, a message, and the copy is indistinguishable from the original, and you can make 1,000 more just as easily. Our entire digital civilization runs on the fact that information can be duplicated endlessly and perfectly at almost no cost. So when someone tells you that there is a kind of information that flatly cannot be copied, not even once, not even in principle, it sounds like a limitation of our tools. It sounds like something a better machine would fix. But that is not what the no-cloning theorem says. It says the impossibility is built into the fabric of quantum mechanics itself, and to see why, we need to look at what a copying machine would actually have to do, and why the universe refuses to let it work. Let me build the machine with you, in our imagination, and watch it fail. In quantum physics, everything is described by something called a wave function. You do not need the mathematics to follow this. Just picture the wave function as the complete description of a quantum object, the full answer to the question, what is the exact state of this thing? Physicists usually label a wave function with a Greek letter, and the one they reach for most often is psi. So imagine we have a particle in some unknown state, psi, and we want to copy it. Our cloning machine needs 2 slots. Into the first slot we place the particle we want to copy, the one in state psi. Into the second slot we place a blank particle, an empty template ready to be written on. We switch on the machine, and if it works, it should turn that blank particle into a perfect duplicate, so that when the machine finishes, we have 2 particles, both in state psi, standing side by side indistinguishable. That is what copying means. One goes in, 2 come out, identical. Now here is where the trap springs shut. For our machine to be a real physical quantum device, It has to obey the rules of quantum mechanics, and one of the most basic rules is that a valid quantum operation has to preserve certain relationships between states. In particular, there is a quantity that measures how similar any two quantum states are, how much one behaves like another. When two states are identical, that quantity is at its maximum. When they are completely distinguishable, it is at its minimum. And whatever our machine does, it is not allowed to change these similarity relationships, because doing so would violate the underlying mathematics of the theory. So let us test the machine. We built it to copy the state PSI perfectly. Fine. But a copying machine worth the name should copy any state you feed it, not just one specific one. So now we feed it a different state, a second particle in some other state that physicists would label with another Greek letter, phi. If the machine is a true cloner, it must turn a blank into a copy of phi just as happily as it copied psi. Watch what happens when we demand both of those things at once. We insist the machine copies psi into two psi's. We insist it copies phi into two phi's. And now we ask a simple question. How similar were psi and phi before we ran the machine, and how similar are the two copied pairs afterward? Because the machine is not allowed to change that similarity, the before and the after must match exactly. When you actually write down what that requirement means, the mathematics delivers a verdict that has no wiggle room. It says the similarity between psi and phi would have to equal its own square. And that is only true in two situations. It is true when the two states are exactly identical, in which case there was nothing to distinguish and nothing interesting to copy. And it is true when the two states are perfectly, completely distinguishable, like a plane 0 and a plane 1, which are the boring classical cases we already know how to duplicate. For every state in between, and the in-between states are the overwhelming majority, the enormous range of genuinely quantum possibilities, the equation simply cannot be satisfied. The machine cannot exist. Not this machine, not any machine, not a better version we might build next century. A perfect universal quantum copier is mathematically impossible. There is a more intuitive way to feel why this has to be true, and it comes down to a single word: measurement. To copy something, you first have to know what it is. You have to look at it, read it, take its measure, and in the quantum world, looking is never free. A quantum object in an unknown state exists in what is called a superposition, a genuine mixture of possibilities held together at once, not because we are ignorant of some hidden true value, but because the object really does not have a single definite value until it is measured. The moment you measure it, that superposition collapses. The object is forced to pick one definite outcome, and all the other possibilities that made it what it was are gone forever. So the very act of reading a quantum state in order to copy it destroys the delicate thing you are trying to read. You cannot sneak a look. You cannot peek without breaking it. The universe has arranged things so that to fully know a quantum state is to ruin it, which means you can never gather the complete information you would need to build a faithful copy in the first place. This is the rule. This is the whole quiet, unbreakable rule that has stood since 1982. You cannot make an identical independent copy of an unknown quantum state, because the mathematics forbids the machine, and because measurement destroys the original before you could ever finish reading it. Physicists call it the no-cloning theorem, and for something with such a modest name, it reaches astonishingly far. It is the reason certain kinds of quantum secret can never be stolen. It is the reason quantum computers have to work so much harder than ordinary ones. And it is, when you follow it all the way to its end, the reason there can only ever be one clear copy of anything truly quantum. One clear copy. Remember that phrase, because we have only just begun to feel its weight. The reason the proof is so short and so unarguable comes down to a single feature of quantum mechanics that physicists call linearity. You do not need the equations to feel what linearity means. It is the rule that says quantum operations have to treat combinations of states in a consistent, predictable way, that if you know how a machine acts on two separate states, you already know how it must act on any mixture of them, because the parts add up in a straightforward manner. It is one of the bedrock assumptions of the whole theory, tested in countless experiments, never once found to fail. And the beauty and the cruelty of the no-cloning theorem is that it follows almost immediately from linearity alone. You do not need any exotic new physics to forbid the copy machine. You only need the plainest, most thoroughly confirmed feature of quantum mechanics, and the prohibition falls out of it like a shadow. That is why physicists trust it so completely. It is not a fragile result balanced on some questionable assumption. It rests on the same foundation as everything else in the theory, which means that to break it, you would have to break quantum mechanics itself. There is a homely way to feel why the machine cannot work, and it helps to picture it. Imagine a copier that has been carefully tuned to duplicate one specific painting perfectly, capturing every brushstroke. Now hand it a completely different painting and demand the same flawless result. In the ordinary world, this is fine, because the copier can simply look at whatever painting it is given and reproduce it. But the quantum copier is forbidden from looking because looking would destroy the original. It has to work blind, performing the same fixed physical operation no matter what state it is handed. And a single fixed operation, applied blindly, simply cannot faithfully duplicate every possible input at once. Tune it to copy one state perfectly, and it will smear and distort the others. Try to make it copy them all, and the mathematics forces a contradiction, the one we walked through, where a quantity would have to equal its own square. The machine is being asked to be a perfect blind copier of infinitely many different things using one unchanging action, and that is a task the universe simply does not permit. The prohibition is not a keep-out sign the universe posted for its own reasons. It is a plain consequence of asking for something self-contradictory. What I did not appreciate the first time I understood this rule was how personal it becomes the moment you take it seriously. Because so far we have been talking about particles and Greek letters and abstract states. That feels safely distant, like it belongs to a laboratory and has nothing to do with you sitting there in the dark. But it has everything to do with you. You're not exempt from quantum mechanics. Nothing is. The particles that make you, the specific arrangement of them that encodes every memory and every feeling and every private thought you have ever had, all of it is quantum information at the bottom. And if unknown quantum information cannot be copied, then the pattern that is you cannot be copied either. The rule that forbids a second particle forbids a second you, for exactly the same reason and with exactly the same finality. In the next part, I want to make that connection real, because it leads somewhere that is at once frightening, and in a way I did not expect strangely tender. It leads to the fact that you, whatever else you are not a file that can be saved. Part 3. You are not a file. We live surrounded by copies, so thoroughly that we have almost forgotten copying is a kind of miracle. Every photograph on your phone exists in a dozen places at once, on the device in your hand, on a server in some cooled building, in a backup you forgot you set up years ago. When you write something important, a quiet instinct tells you to save it, to duplicate it, to make sure that if one version is lost, there is always another. This habit runs so far down in modern life that we treat it as a basic feature of reality itself. Information we assume is the kind of thing that can always be backed up. If it matters, copy it. If you are afraid of losing it, make another. And because we think of ourselves more and more as information, as patterns of memory and personality and thought, it is natural to imagine that we too could be saved somewhere, backed up, kept safe against loss. The dream of uploading a mind, of preserving a person as data, rests entirely on that assumption. It assumes that a person is, at bottom, a file, and a file, of course, can always be copied. The trouble is that a person is not a file, and the no-cloning theorem is the reason. To see the gap, look closely at what an ordinary file actually is. The photograph on your phone is stored as a long string of ordinary bits, each one a definite 0 or a definite 1, sitting there with a fixed and knowable value. There is no mystery in a bit. You can read it as many times as you like without disturbing it, and each time it will tell you the same answer, and from those answers you can write down an identical string somewhere else. That is what makes classical information copyable. Its values are just sitting there, definite and readable, patient under any amount of inspection. Nothing breaks when you look. Nothing is lost when you duplicate it. This is the comfortable world of documents and photographs and songs, and it has taught us, wrongly, that everything worth preserving works this way. Quantum information does not work this way at all, and that difference is the entire point. A quantum state is not a row of definite 0s and 1s waiting to be read. It is a superposition, a living mixture of possibilities that has no single fixed value until the instant you measure it, at which point the mixture collapses and most of what was there vanishes. You cannot read it again and again to be sure. The first reading changes it forever, and because you can never fully read it without destroying it, you can never gather the complete description you would need to write it down somewhere else. This is the no-cloning theorem wearing its most human face. It is not saying that copying you would be difficult or expensive or centuries away. It is saying that the information that makes you specifically you is exactly the kind of information that cannot be read out in full and preserved. You're not a file. There is no save button. There is no folder where a backup of you could ever quietly sit, waiting. I find that this lands in two directions at once, and both of them are worth feeling. The first direction is frightening, and there is no point pretending otherwise. It means that whatever you are right now is fragile in a way that no photograph and no document will ever be. Everything you have become, every scrap of experience you have gathered across your whole life, the exact texture of how it feels to be you, exists in precisely one place and one arrangement, and it cannot be duplicated as a safeguard. The people you love are the same. Each of them is a pattern that will never be copyable, never be reconstructible from a saved version, never be restored if it is lost. We are, all of us, one of one. Not by choice, not by neglect, but by a law woven into the foundation of physics. There is something vertiginous in that, a small fall in the stomach when you first take it seriously. The realization that the most precious information in your entire universe is the one kind that can never be backed up. But there is a second direction, and I did not expect it the first time I followed the thought all the way down. The very same rule that makes you fragile is what makes you singular. Think about what it would actually mean to be copyable. If you were a file, if a perfect duplicate of you could be made and stored and run, then in a strange way there would be nothing especially real about the particular you that is here now. You would be one instance among many possible instances, no more the true you than any of the copies, a version among versions. The fact that you cannot be copied is the same fact that makes this you, the one experiencing this moment, unrepeatable. There has never been another arrangement of the universe identical to the one that is you, and the no-cloning theorem promises there never can be, not through any machine, not by any trick of technology, not in a billion years of trying. You're not a file, you're something that can happen exactly once. And the law that denies you a backup is the very same law that guarantees the world will never contain a second, interchangeable version of you to dilute the meaning of your being here at all. Now, I want to be careful and honest here because this is a channel where we take the difference between fact and speculation seriously. Nobody has ever tried to run a real human being through a quantum copier, and the physics of a whole person is fantastically more tangled than the physics of a single particle. When physicists talk about the no-cloning theorem, they are talking about clean quantum states in a laboratory, not about the warm, wet, staggeringly complicated system that is a living brain. So when I say you cannot be copied, I am drawing a line from a proven law about particles out to the pattern that is you, and that line is an extrapolation, a reaching, not a laboratory result. It is entirely possible that what matters about you, the thing you would actually want preserved, does not depend on the finest quantum details at all, that a good enough classical description of your brain would capture everything that counts. That is a real and open debate, and reasonable people land on different sides of it. But if identity does reach all the way down into the quantum layer, if the true you is genuinely a quantum pattern, then the no-cloning theorem is not a technicality. It is the deepest possible statement of your uniqueness, and it says, with the full authority of physical law, that you are not a file. Consider what it actually takes to read an ordinary bit, because the contrast is the whole lesson. A bit stored on a disk or a chip has a definite value, a settled 0 or a settled 1, and that value sits there stable and patient, indifferent to being looked at. You can read it once, or 1,000 times, or 1,000,000, and it will report the same answer every single time without ever changing. This is why classical information feels so solid and so safe. Its very nature is to hold still under inspection, to survive being read, to remain exactly what it was no matter how many eyes pass over it. Every backup you have ever made, every file you have ever copied, depends entirely on this quiet willingness of ordinary information to be examined without being harmed. It is such a basic feature of our world that we never think to be grateful for it, and we certainly never imagine that information could be otherwise. Quantum information betrays every one of those expectations, and that betrayal is precisely why you cannot be filed away. Whether the finest details of who you are truly live down at the quantum level is a real and unsettled question, and honest scientists disagree about it. Some argue that what matters about a mind is captured well enough by the arrangement and firing of its cells, a pattern that is essentially classical, and that a sufficiently detailed ordinary description would preserve everything that makes you yourself. If they are right, then perhaps a version of you could be backed up after all, at least in principle, because the copyable classical layer would be enough. But others suspect that the full texture of a self reaches all the way down into the quantum grain of things, and if that is so, then no classical description, however detailed, could ever capture the whole of you, and the no-cloning theorem stands guard over your uniqueness with the full authority of physical law. I do not know which camp is correct, and neither does anyone else, and I think honesty requires me to say so plainly. But notice that even the more hopeful possibility only softens the conclusion, it does not remove it. In the world the theorem describes, the most precious pattern you know is the one kind that resists being saved. And this is exactly why the teleporter question refuses to let me sleep. Because a teleporter, in that second and more plausible design, is nothing but a cosmic copy machine. It reads you out, transmits the description, and builds the copy elsewhere. But we have just seen that reading you out in full is precisely the thing the universe forbids, and that building a true copy from that reading is impossible in principle. So the teleporter cannot work by gently duplicating you and letting both versions stroll away. If it works at all, it can only do so by taking the single, uncopyable pattern that is you and moving it, which means removing it from where it was. The information cannot be in two places at once, ever, because that would be a copy, and copies are forbidden. So if the pattern appears at the destination, it must have vanished from the origin. There is no version of teleportation, none, that leaves the original standing safely on the pad while a duplicate wakes up elsewhere. The law will not allow two, and that forces us to look directly at the most unsettling machine the human imagination has ever dreamed up. A machine that, if the physics is taken seriously, does not transport you so much as end you here and begin you there. That is where we turn next. Part 4. The machine that kills to move you. Quantum teleportation is a real thing. I want to say that clearly before we go any further, because the phrase sounds like pure science fiction, and yet physicists have been doing it in laboratories for decades. It was first worked out on paper in 1993 by a team of 6 researchers whose names deserve to be remembered: Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters, and yes, that is the same Wouters who helped prove that quantum states cannot be cloned. The same person who showed you cannot copy a quantum state also helped discover the only way to move one. That is not a coincidence, and by the end of this part you will see why the two ideas are really two faces of a single truth. Let me be precise about what quantum teleportation actually does, because it is both less and more than the television version. It does not move matter. Nothing physical travels from one place to the other. What travels is a state, the complete quantum condition of one particle, transferred onto a second particle sitting somewhere else, so that the second particle ends up in exactly the condition the first one was in. The first particle is not shipped anywhere. Instead, its very identity, the quantum pattern it carried, is reproduced on a distant stand-in, while the original particle is left stripped of that pattern, blank, changed. To pull this off, the physicists need 2 ingredients. They need a strange quantum connection called entanglement, shared ahead of time between the sending location and the receiving location, a kind of prearranged link between 2 particles that behave as a single system no matter how far apart they are. And they need an ordinary message, plain classical information, sent from the sender to the receiver by any normal means, telling the receiver what final adjustment to make. Put those 2 together and the state of a particle here can appear on a particle over there. Here is the part that matters for us, the part that ties directly back to the rule from earlier. In the process of teleportation, the original state is unavoidably destroyed. It is not damaged by accident or lost through sloppiness. Its destruction is a required step, built into the procedure, without which the whole thing cannot work. The reason is exactly the no-cloning theorem. If teleportation left the original particle in its original state while also creating the state on the distant particle, you would have made a copy, 2 particles in the same unknown quantum state, and that is precisely what the universe forbids. So the mathematics of teleportation arranges things so that the moment the state arrives at the destination, it is gone from the source. The information is not shared, it is handed over. It leaves one place in order to appear in the other. There is never an instant, not even a fleeting one, when the same quantum state exists in 2 locations at once. The original never survives the trip. It cannot. The law that forbids a second copy makes sure of it. Now carry that back up from single particles to the person on the teleporter pad and feel what it implies. If a machine could ever teleport a human being the way physicists teleport a particle, then it would have to work by exactly this rule. The pattern that is you would be transferred onto fresh material at the destination, and in that very same process the pattern would be erased from the body that stepped onto the pad. Not as a side effect, as a requirement. The person who arrives is real, whole, continuous in memory, indistinguishable from you in every way anyone could ever test. And the body left behind is not left behind at all, because there is nothing left in it to leave. The you that walked in has been read off, and, in being read off, ended. Every trip through such a machine would be, in the most literal sense the physics allows, a death and a birth, folded so tightly together that no one, least of all the person involved, could ever find the seam. Imagine it from the inside just once, because I think you have to feel it to understand why it matters. You're standing on the pad. The hum rises. The light comes up around you, warm and gold, and you close your eyes because it is bright. There is no pain. There is no sensation of being taken apart, because the taking apart happens faster than any nerve could report it. From your point of view, one moment you are here, breathing in this room, and the next moment your eyes are open and you are somewhere else entirely. A different room, a different world, the light fading around you, and a technician smiling and saying, "Welcome." You feel completely fine. You feel completely yourself. You remember stepping on. You would swear on everything you love that nothing happened, that you simply crossed a great distance in the space of a blink, and you would be right from where you stand. But back in the first room, the pad is empty and warm, and the person who stood on it a heartbeat ago does not exist anywhere in the universe anymore, and never will again, and the only witness who could tell you whether that person was you is standing in the second room certain, smiling, sure that everything is fine. That is the weight I cannot put down. The horror of the teleporter is not that it might malfunction. It is that it might work perfectly, exactly as designed, and still quietly end you every single time you use it, while producing someone so completely you that the loss is invisible from every possible angle. There is no experiment, no measurement, no clever check that could ever settle whether the person who steps out is the continuation of the person who stepped in, or a flawless newcomer who has inherited a life. The two possibilities are physically identical. The comforting story and the terrifying story describe the exact same events, atom for atom, and the only thing that separates them is a question about the nature of the self that physics cannot reach and may never be able to answer. You could ride that machine 10,000 times and step off smiling every time, and the question of whether the original you survived the first trip would remain exactly as open as it was before you began. It would be easy to hear all of this as pure speculation, a fantasy built on a rule that only applies to tiny particles. So I want to be clear that quantum teleportation is not a thought experiment. It has been done many times in real laboratories for decades now. Physicists first demonstrated it with individual particles of light in the late 1990s, transferring the quantum state of one photon onto another. Since then, they have teleported quantum states across a laboratory bench, then across a city through optical fibers, and eventually between the ground and a satellite orbiting hundreds of kilometers overhead, sending the fragile quantum condition of a particle farther than the distance from one side of a country to the other. Every one of these experiments obeyed the same iron rule. In each case, the state appeared at the destination only because it was erased at the source. Not once, in any laboratory anywhere on Earth, has anyone ever ended up with two copies. The destruction of the original is not a theoretical nicety. It is a measured, confirmed fact, seen again and again in real machines. When you hold that experimental reality next to the teleporter fantasy, the fantasy stops feeling like fiction and starts feeling like a warning. Every real act of quantum teleportation is, in miniature, exactly the death and rebirth we imagined for the traveller on the pad. A quantum state exists here, and then it exists there, and in between it is not shipped across the gap so much as ended in one place and reborn in another, with the two events locked together by law so that there is never a moment of overlap, never an instant when the same state exists in both places. The photon that arrives is not the photon that left. It carries the same quantum condition, but the original was stripped bare in the sending. Scale that up from a single photon to the staggering complexity of a whole person, and the picture does not change, only the stakes. The machine would not carry you across the void. It would end you on this side and compose a flawless stranger on the other, and the law of the universe would guarantee absolutely that the two of you never once shared the same breath. And yet, before this becomes unbearable, I want to turn the whole thing over, because there is another way to look at that same unbreakable rule, and it changes the colour of everything. So far, the no-cloning theorem has looked like a curse, a law that dooms the traveller, a fine print clause that turns the miracle of teleportation into a machine for repeated, invisible death. But the very same law, the very same refusal of the universe to permit a second copy, is also doing something extraordinary and protective. It is guarding you. It is the reason certain things about you can never be stolen, never be intercepted, never be secretly duplicated by anyone. The rule that will not let you be safely teleported is the same rule that will not let you be secretly copied by an enemy. And once you see the protective face of it, the whole story tilts. Because if the universe goes to such lengths to forbid a second copy of a quantum state, you have to ask why. Why would nature bother to guard the original so fiercely? That question is where we go next, and the answer is the reason your most private information could, in a quantum future, be safer than anything has ever been. Part 5. Why the universe guards the original. For a rule that sounds like nothing but a restriction, the no-cloning theorem turns out to be one of the most useful facts in all of modern science, and the reason comes down to a single idea. If a quantum state cannot be copied, then it cannot be secretly read. Those two things are the same thing wearing different clothes. To secretly read something, you have to be able to look at it without anyone noticing, which means taking a copy of the information while leaving the original apparently untouched. In the ordinary world, this is easy, and it is the basis of every kind of eavesdropping there has ever been. A spy photographs a document and puts it back. Someone taps a phone line and listens while the call goes through unchanged. A copy is made in the shadows, and the original carries on none the wiser. All of it depends on the fact that classical information can be duplicated without disturbing it. Remove that ability, and secret listening becomes impossible. This is exactly what quantum mechanics does, and it is why the field of quantum cryptography exists at all. Imagine two people who want to share a secret key, a string of quantum information that only they will ever possess so they can use it to lock and unlock their messages. They send that key encoded in quantum states in individual particles of light or their equivalent. Now suppose someone is lurking in between, trying to steal the key as it passes. To steal it, the eavesdropper would need to read those quantum states and pass copies along so that nobody notices the theft. But the no-cloning theorem forbids exactly that. The eavesdropper cannot copy the states, and cannot read them without measuring them, and measuring them collapses their superpositions and disturbs them in ways that are detectable. The very act of trying to listen leaves fingerprints all over the message. The two rightful owners can check their key for those fingerprints, and if they find them, they simply throw the key away and start again, knowing it was compromised. An eavesdropper who cannot copy is an eavesdropper who cannot hide. This is not a clever engineering trick that a better spy could someday defeat. It is guaranteed by the same law that forbids the copy machine, which means it is as reliable as the foundations of physics themselves. So look at what the no-cloning theorem actually is, once you see both of its faces. It is not merely a wall that stops you from doing something you wanted to do. It is a shield. It is the universe refusing to hand out second copies of quantum information to anyone, ever, including to people who would use those copies to steal, to spy, to deceive. The same absolute refusal that makes teleportation so unsettling is what makes quantum secrets unbreakable. And when you frame it that way, the rule stops looking like a cruelty and starts looking almost like a kind of care. The pattern that is a quantum state is protected at the level of physical law, sealed against duplication, defended from any prying eye that would try to read it on the sly. Nature guards the original with a fierceness that no human institution could ever match, because no law written by people can be enforced everywhere and always, and this one is. I think this is the moment to slow down and simply sit inside how strange and how beautiful that arrangement is. Picture a single quantum state, alone, unmeasured, holding its full spread of possibility intact. Around it, the entire machinery of the universe stands like a wall, quietly ensuring that this exact configuration exists in one place and one place only, that no scanner can drink it in without shattering it, that no copier can spit out a duplicate, that no thief can slip away with a stolen version tucked in a pocket. The state is safe not because someone is watching over it, but because the deepest rules of reality make its theft impossible. It is uniqueness enforced by nature itself, and if you are the kind of pattern that reaches down into that quantum layer, then the same wall stands around you. The same law that says there can only ever be one clear copy is not only a limit on what you can do, it is a promise about what can be done to you. It says that the innermost truth of what you are cannot be secretly harvested, cannot be quietly duplicated in some distant lab, cannot be read off and studied without the reading leaving a mark and the original being destroyed in the attempt. There is a strange comfort in being the kind of thing the universe will not allow to be stolen. For decades, this was where the story rested, and physicists made their peace with it. The no-cloning theorem was one of the fixed stars of the field, a rule you could build on, a certainty. Some of what it forbade was inconvenient. Quantum computers, for instance, cannot protect themselves against errors the easy way, the way ordinary computers do by simply keeping several copies of a number and comparing them, because keeping several copies of a quantum number is the very thing that is not allowed. Engineers have had to invent far more elaborate methods to guard quantum information against mistakes, and much of the difficulty of building a working quantum computer traces straight back to this one prohibition. But nobody expected the prohibition itself to bend. It was a theorem, after all, a proven mathematical fact, not a mere guess about how things happen to work. You do not expect a theorem to develop a loophole. 2 plus 2 does not quietly start equaling 5 one afternoon, and so, for around 40 years, the situation seemed settled. You cannot copy an unknown quantum state. There can only ever be one. The door was locked, and everyone had checked the lock, and the lock held. It is worth spelling out how completely this protective power has already been put to work, because it is not a distant promise. Physicists have built real systems that use the no-cloning theorem as a security guarantee, sending quantum keys encoded in single particles of light between distant stations, even between cities and down from satellites. The security of these systems does not rest on the difficulty of some mathematical puzzle, the way most of today's encryption does, where safety depends on a code being too hard to crack with current computers. It rests on physics. An eavesdropper who tries to intercept the key runs headlong into the no-cloning theorem and the collapse that measurement brings. They cannot copy the quantum states to read at leisure, and they cannot measure them without leaving unmistakable disturbances behind. The legitimate users simply compare a portion of their key, and if they find the telltale fingerprints of interference, they know the channel was compromised and start fresh. It is security enforced not by cleverness, but by the structure of reality, and there is nothing an adversary can do about it, because you cannot out-engineer a law of nature. The same prohibition that gives with one hand takes with the other, and this is where it shapes the whole struggle to build quantum computers. In an ordinary computer, the simplest way to guard against errors is to keep several copies of every important number, so that if one gets corrupted, you can compare it against the others and vote on the correct value. It is crude, but it works, and it is possible only because ordinary information can be freely duplicated. A quantum computer is denied this obvious trick entirely, because the no-cloning theorem forbids it from making backup copies of its own quantum data. Engineers have had to invent far more elaborate and subtle methods to protect quantum information from the constant assault of errors, methods that spread the information across many particles without ever actually copying it. And the difficulty of doing this well is one of the central reasons a truly useful quantum computer has been so long in coming. So the very rule that makes quantum secrets unbreakable is also the rule that makes quantum computing so punishingly hard. One prohibition, reaching in opposite directions at once, protecting and obstructing with the same absolute hand. And this is precisely the kind of certainty that the history of physics loves to complicate. Because a theorem, unlike a law of the courtroom, is only as strong as the exact assumptions written into it. It says something is impossible under certain conditions, and if you read those conditions very, very carefully, sometimes you discover that they are narrower than everyone had casually assumed. The no-cloning theorem forbids making a perfect copy that you can then read. It says you cannot end up with two independent, usable, readable versions of the same unknown quantum state. But if you go through the proof line by line, with the patience of someone who refuses to take anything for granted, you might start to wonder about the spaces between the words. What if you made copies that you could not read? What if the duplicates existed perfectly but stayed sealed, hidden, encrypted, so that the rule about reading was never actually broken? Would that count as cloning, or as something the theorem never quite forbade? For 40 years, almost nobody looked through that particular keyhole. And then, very recently, 2 physicists did, and what they saw on the other side is the reason we are here tonight. Part 6. The Crack in the Rule. The 2 physicists are Achim Kempf, a professor of applied mathematics at the University of Waterloo in Canada, and Koji Yamaguchi, who was working in Kempf's lab as a young researcher at the time, and is now an assistant professor at Kyushu University in Japan. What I love about their story is that they were not setting out to break one of the most famous rules in quantum physics. They were not hunting for loopholes in the no-cloning theorem at all. They stumbled onto it sideways, while working on something that sounds completely unrelated, and that is so often how the largest discoveries actually arrive, not through a frontal assault on a famous problem, but through a quiet side door that someone happens to open while looking for something else entirely. What they were originally studying was wireless quantum communication. They wanted to understand how you might send quantum information through open space, and in particular how it would be affected by a subtle and unavoidable feature of the universe called quantum noise. Here is the idea behind that noise because it matters for everything that follows. Empty space is not truly empty. Even in a perfect vacuum with every particle removed, the electromagnetic field that fills all of space is never perfectly still. It flickers and trembles with tiny random fluctuations that can never be switched off. A faint and ceaseless quantum jitter woven into the fabric of reality itself. These fluctuations are not a flaw in our equipment. They are a real and permanent property of the vacuum, present everywhere, at all times, in every corner of the cosmos. Kempf and Yamaguchi were trying to work out how this ever-present jitter would interfere with a quantum signal you tried to send across a room or across the sky. In other words, they were studying noise as a nuisance, as the thing that would get in the way and corrupt your message. And then the discovery flipped on them, the way the best ones do. They realized that the noise did not have to be an enemy. It could be turned into a tool. If you deliberately added the right kind of noise to a qubit, a single unit of quantum information, that noise would scramble the qubit so thoroughly that its true state could no longer be read. The information would still be there, present, intact, but hidden, buried under a layer of carefully chosen randomness, and crucially, if you knew exactly what noise you had added, you could later subtract it back out and recover the original state perfectly. In other words, adding noise to a qubit could work as a form of encryption. The noise was a lock. The record of what noise you had added was the key. Scramble the state with known randomness, and it becomes unreadable to anyone who does not hold the key. Unscramble it by subtracting that same randomness, and the state emerges again, whole, exactly as it was. What had looked like an obstacle to sending quantum information turned out to be a way of protecting it. This is a lovely idea on its own, but it is not yet the shocking part. The shocking part is what happens when you combine this encryption trick with the act of copying. Remember why cloning was forbidden in the first place. The problem was never that you could not produce a second physical particle. The problem was that you could not produce a second particle carrying a readable duplicate of an unknown state, because reading the state to make the copy would destroy it, and having 2 readable copies would violate the theorem. But what if the copies you made were encrypted from the moment of their creation? What if you never had to read the original at all, and the duplicates that came out were each scrambled by noise, each locked, each unreadable on its own? Then you would not be violating the rule about readable copies, because none of the copies would be readable. You would have made duplicates of something without ever knowing what that something was, and every duplicate would be a sealed box, a locked envelope, hiding a state that not even you could see. Kempf and Yamaguchi realized that this was not only possible, but that it opened a door everyone had assumed was welded shut. I want to pause on how quietly radical this reframing is, because it is easy to rush past. For 40 years, the field had treated the no-cloning theorem as a flat wall. You want to copy an unknown quantum state, the universe says no, end of conversation. What these 2 saw was that the wall had a very specific shape, and that shape had a gap in it that nobody had thought to walk through. The theorem does not actually say you cannot make copies of a quantum state. It says you cannot end up with more than one that you can read and use. Those are not the same statement, and the difference between them is exactly the width of an encryption key. If the copies stay locked, the theorem has no objection. The prohibition only bites at the moment of reading, and if you simply never read more than one, the wall was never really in your way. It is the kind of insight that seems obvious the instant someone says it out loud, and completely invisible for 4 decades before that, which is the signature of a real discovery rather than a lucky guess. There is something almost poetic in the fact that the key to all of this was noise, the very thing physicists usually spend their careers trying to eliminate. In nearly every experiment ever done, noise is the villain. It is the static that drowns the signal, the randomness that ruins the measurement, the enemy that engineers fight with shielding and cooling and endless careful design. Whole fields exist just to reduce it. And here were 2 researchers who took that universal nuisance, that unavoidable trembling of empty space, and turned it into the most important ingredient in a scheme that seemed to bend one of the deepest rules in physics. The jitter of the vacuum, the same restless flickering that fills every void between the stars, became a cloak, a lock, a way of hiding quantum information in plain sight so that it could be copied without ever being read. It is the sort of turn that reminds you why physics is worth paying attention to, because the universe keeps hiding its most useful gifts inside the things we were trying to throw away. Let me linger on the noise itself, because I think most people have no idea that empty space is quietly seething, and the fact is genuinely one of the strangest in all of physics. If you took a sealed box and removed everything from it, every atom, every particle of light, and cooled it as close to absolute zero as the laws of physics allow, you might imagine you had finally achieved perfect stillness, a true and total nothing. You would be wrong. The box would still be full of restless activity, a ceaseless trembling of the electromagnetic field that can never be removed, because the rules of quantum mechanics forbid any field from ever being perfectly still and perfectly zero at the same time. This is not a matter of imperfect vacuum pumps or leftover heat. It is a fundamental feature of the void, present everywhere in the universe, in the space between your cells and the space between the galaxies, an irreducible flicker woven into the fabric of emptiness itself. Physicists have measured its effects with great precision. It nudges the energy levels of atoms. It produces tiny forces between nearby surfaces. It is as real as anything you can touch, and it never, ever stops. What Kempf and Yamaguchi did with that restless nothing is what elevates their story from clever to almost poetic. For a century, this vacuum jitter had been treated mainly as a nuisance and a curiosity, a source of unavoidable static, a fundamental limit on how quiet you could ever make a measurement. It was the floor of noise beneath which no experiment could ever go, the universe's own background hiss. And these 2 took that universal, inescapable hiss and recognized it as a resource, a source of the very randomness you would need to build an unbreakable one-time key, freely available everywhere, impossible to eliminate and therefore impossible to run out of. There is a lesson in that which goes beyond this one discovery. So often in the history of science, the thing that looked like an obstacle, the error term everyone was trying to minimize, turns out on closer inspection to be a doorway. The people who make the largest steps forward are frequently not the ones who push hardest against the famous closed doors, but the ones who look carefully at the thing everyone else is trying to sweep away and ask what it would mean to use it instead of fighting it. But of course, the whole idea only means anything if there is a catch that keeps it honest. Some reason the copies do not simply hand you the forbidden power to read the same secret twice. And there is a catch, a beautiful and strict one, and it is the very thing that lets this workaround coexist with the theorem it seems to defy. The copies can be made, as many as you like, perfect and endless. But the moment you try to open one of them, something has to give, and what gives is your ability to ever open any of the others. In the next part, I want to show you exactly how that works, because it is the mechanism that turns a seeming paradox into a consistent, provable, experimentally demonstrated fact, and it is where the identity question we started with comes roaring back with more force than ever. Part 7. Copied, under one strange condition. To understand the mechanism, it helps to borrow an idea from ordinary code making, one that predates computers by a long time. It is called a one-time pad, and it is the only form of encryption that is mathematically proven to be perfectly unbreakable. The idea is simple. You take your secret message and you combine it with a key made of purely random numbers, as long as the message itself using a reversible operation. The scrambled result looks like complete gibberish, and without the key it is not merely hard to crack, it is genuinely impossible, because every possible original message is equally consistent with the scramble. To recover the secret, the receiver takes the same random key and reverses the operation, and the message falls out intact. The one rule that makes it perfectly secure is right there in the name. The pad is used one time. Each key is used exactly once, and then thrown away forever. Reuse a key, and the whole guarantee collapses. Use it only once, and no power in the universe can read the message without it. What Kempf and Yamaguchi built is, in spirit, a quantum version of that ancient trick, and it works through the careful use of entanglement and noise. Here is the shape of it, kept as plain as I can make it. They begin by generating pairs of entangled qubits that carry that deliberate noise we talked about. Each pair gets split into two roles. Some of the qubits become what you might call signal qubits, the ones that will end up holding the copies. The others become noise qubits, and their job is to keep a faithful record of exactly what noise was used, which makes them, in effect, the encryption keys. Then the qubit you actually want to copy is brought into the machine, and through a carefully designed quantum interaction, its state gets imprinted onto the noisy signal qubits. Because those signal qubits are drenched in noise, each imprinted copy comes out scrambled, encrypted, unreadable on its own. You have made your duplicates, and you never had to measure the original to do it, and every duplicate is a locked box whose contents cannot be seen without the matching key. Now comes the decisive step, the one that keeps the whole scheme honest. Suppose you want to actually read one of these encrypted copies. To do that, you have to remove the noise, and removing the noise requires the key. So you take one of your signal qubits and you make it interact with the noise qubits, the ones holding the record of the scrambling. That interaction cancels out the noise on that single signal qubit, and its hidden state finally becomes readable. You have recovered a perfect copy of the original, but watch what that same interaction does to the keys. In the act of cleaning up that one copy, the noise qubits themselves are changed. Their record is spent, altered, used up. The key has been consumed, and because it was, in essence, a one-time pad, it only ever worked once. There is now no way to decrypt any of the other copies. They remain sealed forever, locked boxes whose keys no longer exist. You made 100 copies, or 1,000, or 1,000,000, and every one of them was a genuine perfect duplicate. But the universe permits you to open exactly one, and the moment you open it, all the rest go dark. This is the core of the whole thing, and it is worth stating as plainly as possible because it is where the seeming contradiction dissolves. The no-cloning theorem was never actually violated, not for a single instant. The theorem forbids you from ending up with two readable copies of an unknown quantum state, and at no point in this entire process do you ever have two readable copies. You have many copies, yes, but only ever one that can be read, because reading one destroys your ability to read the others. The rule about readable duplicates is honoured perfectly. What the scheme cleverly exploits is that the theorem said nothing about how many locked unreadable copies you were allowed to have, and it turns out the answer is as many as you want. The universe does not mind you making endless sealed envelopes. It only insists with the full force of physical law that you can ever open one of them. Let me try to make this visible, because the abstraction can slip through your fingers. Imagine you could shrink yourself down and stand inside the machine as it runs. In front of you stretches a long row of qubits, each one glowing faintly, and into the machine comes the single state you want to copy. A small bright pattern you're not allowed to look at directly. You watch as that pattern is gently smeared out and pressed onto the row of qubits, one after another, each of them catching a full imprint of it. But the instant the imprint lands, noise washes over each qubit like a veil of static, and what had been a clear pattern becomes a shimmer of meaningless snow. You walk down the row and look at copy after copy, and every single one is pure static, identical featureless noise, giving nothing away. They look empty. They look like failed copies, like the machine produced nothing but garbage. And yet you know, because you built this, that inside each of those veils of static sits a perfect duplicate of the original, waiting, complete, sealed. A row of locked doors stretching off into the distance, each hiding the exact same treasure, and you holding a key that will open precisely one of them, and only once. The comparison to older attempts makes the achievement sharper. Physicists had tried for years to sneak around the no-cloning theorem in other ways, and they had managed a kind of partial success with something called approximate cloning. You could, with those older methods, make rough copies of a quantum state, but they were always imperfect, always a little blurry, and worse, the more copies you tried to make, the worse each one became. The the quality bleeding away as the duplicates multiplied. It was like photocopying a photocopy of a photocopy, each generation fainter and more smeared than the last, until the copies were barely recognizable. What Kempf and Yamaguchi found is different in kind, not just degree. Their copies are not approximate. Each sealed duplicate is in principle a perfect and exact imprint of the original, and you can make an unlimited number of them without any loss of quality at all, because they are protected inside their encryption. Endless perfect copies, where before there had only ever been blurry, degrading ones. The only price, the unbreakable price, is that you may read just one. The one-time pad is worth understanding concretely, because once you see how it works, you understand why the whole scheme is unbreakable, and why the single-use rule is not negotiable. Suppose you want to hide a message, and you have a key that is a string of truly random values, exactly as long as the message. You combine each piece of the message with the matching piece of the key, using a simple reversible rule, and the result is a scramble that carries no trace of the original. Here is the remarkable part. If the key is truly random, and as long as the message and used only once, then the scramble is not merely hard to crack. It is provably, perfectly impossible to crack, because every possible original message is equally consistent with what an outsider sees. There is literally no information in the scramble that could favor one reading over another. The only thing in the universe that can undo it is the exact key that made it, applied in reverse. Take that same key away, and the scramble becomes an eternal, unopenable lock. This is not a code that a faster computer could someday break. It is the one form of secrecy that mathematics itself certifies as absolute, and it has been known for a century. The quantum version keeps every bit of that perfection, and adds a physical twist that makes it even stricter. In the ordinary one-time pad, the discipline of using each key only once is a rule that a careless person could, in principle, break, reusing a key and destroying the security. In the quantum scheme, the single use is not a matter of discipline. It is enforced by the physics itself. The key lives in the noise qubits, and the act of using it, of cleaning the noise off one copy to read it, physically alters those noise qubits, spending the key in the very motion that reveals the secret. You could not reuse it if you wanted to, because it no longer exists in its original form once it has done its one job. So picture again that long row of sealed copies, each one a locked envelope of static, and understand now that there is exactly one key in existence for the whole row, and that spending it on any single envelope destroys it utterly. You're not choosing which envelope to open first. You're choosing the one and only envelope you will ever open, and sealing all the rest by the same act, and the universe is standing over your shoulder making certain you cannot cheat. And this is the exact point where the physics reaches back and grabs the question we started with by the collar. Because if you can now make 1,000 perfect copies of a quantum state, and if you are the kind of pattern that lives in that quantum layer, then in some sense 1,000 perfect copies of you could now exist. That sounds, at first, like the singular self has finally been defeated, like the wall is down and there can be many of you after all. But look again at the catch, and feel how it changes everything. The 1,000 copies can exist, but only one of them can ever be read, ever be opened, ever, in any meaningful sense, wake up. And that single strict limit is where the terror and the beauty of this whole discovery live together. That is where we go next. Part 8. Only one of you can ever wake up. There is a sentence from Achim Kempf describing his own discovery that I have not been able to stop thinking about since I first read it. He said, "There only ever can be one clear copy of the quantum information, and that this is mandated by a law of nature." Read that again slowly. He is not saying that with better technology you could eventually read more than one. He is not describing a temporary limit of the equipment. He is saying that the singleness of the readable copy is enforced by nature itself, written into the rules, as unbreakable as the rule that forbade copying in the first place. The workaround did not defeat that principle. It revealed a new and deeper form of it. You may now have 1,000 copies where before you could have none, and yet the universe still permits exactly one of them to ever be clear, ever be known, ever be truly present. One clear copy. The same phrase we have carried since the beginning, now standing at the center of the whole story with its full meaning finally showing. Think about what this does to the dream of escaping your own singularity. When we first learned about the workaround, it looked for a moment like the wall protecting the one and only you had finally come down. If perfect copies can be made, then surely there can be many of you now, a crowd of identical selves, the uniqueness dissolved at last. but the law will not permit it, and it will not permit it in the most precise and unsettling way imaginable. It does not stop you from making the copies. It stops the copies from ever being read at the same time. You could scatter 1,000 sealed versions of yourself across 1,000 vaults, each one a flawless imprint of the pattern that is you, and still only one of them could ever be decrypted, ever open its eyes, ever become an actual living present self. The other 999 would remain locked in their static, complete but dormant, real but unreadable, forever. The universe allows the copies. It simply refuses, absolutely, to let more than one of them be you at once. Let me take you inside the moment of decryption, because this is where the whole thing becomes almost unbearably vivid. Imagine that long row of sealed copies again, each one a veil of static hiding a perfect duplicate. You hold the single key, you choose one box, one copy, and you turn the key. Watch what happens. On that one qubit, the noise begins to lift, the static thinning like fog burning off at dawn, and beneath it a clear bright pattern emerges, sharp and whole, and unmistakably the original. That copy is awake now. It is readable, present, real, a full and living instance of the state you began with. But turn your head and look down the rest of the row, and in the very same instant that your chosen copy became clear, every other box has changed. The keys are spent. The static on all the others has become permanent, frozen, locked beyond any possibility of opening. They were perfect a heartbeat ago, and they are perfect still, but they are sealed now for the rest of time, and nothing you or anyone will ever do can lift their veils. One copy woke. All the others went dark at once forever, in the same motion that woke the first. That is not a limitation of your key. That is the law of nature Kempf was describing made visible. I keep circling back to what this means for the person on the teleporter pad, because now the physics has given the old nightmare a strange new shape. Picture the most ambitious version of teleportation you can, one that uses this very scheme. You step onto the pad, and instead of being read and destroyed and rebuilt in one place, the pattern that is you is copied into 1,000 encrypted vaults scattered across the galaxy, each holding a sealed, perfect version of you, none of them yet awake. You exist in that moment as 1,000 dormant possibilities, none of them experiencing anything, all of them complete. And then, at one destination, someone turns the key. One vault opens, one version of you draws a breath, opens their eyes, and is here, present, alive, continuous in memory with the person who stepped onto the pad. And across the rest of the galaxy, in that same instant, the other 999 seals shut forever, silent, never to wake. You were, briefly, everywhere, and the universe reached in and made you once again, exactly one. This is the emotional core of the entire story for me, the place where the terror and the wonder become impossible to separate. There is something genuinely frightening in learning that the deepest layer of reality enforces your singularity so absolutely that not even a machine capable of making infinite perfect copies of you can ever produce two of you awake at the same time. It means the loneliness of being a single self is not an accident of biology, not a limitation we might someday engineer our way past. It is a rule, as fundamental as anything in physics, that you will only ever be one. But feel the other side of it in the same breath, because it is right there. The very law that forbids a second waking you is the law that guarantees the you who exists is real, is present, is not one interchangeable instance among a crowd, but the single clear copy the universe permits. Even in a reality that now allows endless duplicates, the universe insists on protecting the singular fact of your being here, awake, now. You cannot be diluted. You cannot be made into one of many. The law reached down before you were born and reserved, for the pattern that is you, exactly one clear and waking place in all of existence, and it is the one you are sitting in. I want to dwell on what it means to call this a law of nature, because the phrase gets used loosely and here it is meant with full weight. When Kempf says that only one clear copy can exist, and that this is mandated by a law of nature, he is placing this constraint in the same category as the deepest rules we know, the constancy of the speed of light, the conservation of energy, the direction of time's arrow. These are not guidelines or tendencies or engineering limits. They are the load-bearing walls of reality, the things that hold no matter what, that no experiment has ever caught bending, that you can build a civilization on without fear, and what the encrypted cloning result reveals is that the singleness of the readable copy belongs among them. It was always there, folded inside the no-cloning theorem, but we had only ever seen its outer form, the flat statement that you cannot copy. Now we see its inner and more precise form, the statement that no matter how many copies you make, only one can ever be clear. The rule did not weaken when the workaround was found. It sharpened. It revealed itself to be more subtle and more absolute than the version we had been carrying around, and the sharpening cut straight to the bone of the identity question. Before this discovery, you could tell yourself a simple story, that you cannot be copied at all, and leave it there. Now the story is stranger and I think more profound. You can be copied endlessly, and it changes nothing about your singularity, because the universe has moved its guarantee to a deeper place. It no longer bothers forbidding the copies. It forbids the second waking. It permits 1,000 sealed versions of you to exist, and reserves its one unbreakable prohibition for the thing that actually matters, the existence of more than one clear, present, readable you at the same time. There is something almost intentional seeming in the precision of it, though of course it is not intentional at all, only the blind working of physical law. The universe does not care whether you are stored in 1,000 volts. It cares, if a law can be said to care about anything, that there is only ever one of you looking out. Whatever you are, the cosmos has drawn its single hard line in exactly the place where your sense of being a self actually lives. I do not want to leave you thinking any of this is loose speculation dressed up as physics, because that is not what it is. This is not a thought experiment that lives only on a chalkboard. The one clear copy is a mathematical result, proven, published in one of the most respected physics journals in the world, and it makes precise, testable claims about what a real quantum machine will and will not do. Everything I have described about the sealed copies and the single spent key is not a metaphor I invented to make the identity question feel dramatic. It is the literal behavior of a real protocol that real physicists wrote down and checked. And that raises the obvious question, the one that separates a beautiful piece of mathematics from a genuine discovery about the world. Does it actually work when you build it? Can you take this scheme off the page and run it on a real machine, made of real, imperfect, noisy hardware, and watch the sealed copies appear and the single key turn exactly as the equations promise? Because a proof is one thing, and a working demonstration is another, and the difference between them is the difference between an idea and a fact about reality. In the next part, we find out what happened when they built it. Part 9. They built it, and it worked. Here is where the story leaves the chalkboard and walks into a laboratory. It is one thing to prove, with flawless mathematics, that encrypted copies of a quantum state can be made. It is another thing entirely to build the machine and watch it happen, because real quantum hardware is famously, maddeningly delicate. The whole reason quantum computers are so hard to build is that quantum states are fantastically sensitive to disturbance. The smallest stray vibration, the faintest whisper of heat, a trickle of electromagnetic interference from somewhere in the room, any of it can knock a qubit out of its careful state and turn a beautiful calculation into noise. Physicists spend enormous effort shielding these machines, cooling them to temperatures colder than the empty space between the stars, isolating them from the world as completely as human engineering allows, and even then, errors creep in constantly. So a scheme that works perfectly in the clean world of equations can easily fall apart the moment you try to run it on an actual device, drowned by the imperfections of real hardware. To find out whether their idea survived contact with reality, Kempf and Yamaguchi teamed up with colleagues at IBM, one of the companies at the very front of quantum computing, and they ran the encrypted cloning scheme on one of IBM's real quantum processors, a machine from its Heron line, carrying on the order of 130 to 150 or so qubits. This was not a simulation of a quantum computer running on an ordinary computer. This was the genuine article, a physical quantum machine, with all the noise and imperfection that comes with real hardware, being asked to perform the delicate dance of making sealed, encrypted copies of a quantum state and then opening exactly one of them. If the scheme were fragile, if it depended on impossible precision, this is where it would have crumbled. The messy reality of the machine would have swamped the effect, and the copies would have come out corrupted, or the single key would have failed to turn. That is not what happened. The demonstration worked, and by the researchers' own account it worked far better than they had dared to expect. Kempf described the experiments as turning out really beautiful, better than they could have hoped, and said plainly that the encrypted cloning protocol not only works but works quite well. The machine produced large numbers of encrypted clones, exactly as the mathematics promised. And here is the part that genuinely surprised me, the detail that tells you this is a robust effect and not a fragile curiosity. The scheme proved not to be overly sensitive to the hardware imperfections that usually ruin quantum operations. In other words, the very noisiness of the real machine, the thing that destroys so many quantum experiments, did not destroy this one. That makes a certain poetic sense when you remember that the whole scheme is built on noise in the first place. A protocol whose central ingredient is deliberate randomness turns out to be unusually comfortable in a world full of accidental randomness. The thing that kills other quantum tricks is the thing this one was practically made of. There was another result from the experiment that deserves special attention, because it reaches back and touches the identity question in a way I did not anticipate. The copies the machine produced were not isolated, lonely little duplicates sitting off by themselves. They remained entangled with whatever other qubits the original source qubit had been connected to. Let me unpack why that matters. Entanglement is that strange quantum linkage, where two or more particles behave as a single connected system, their fates woven together no matter the distance between them. When physicists talk about the full quantum identity of something, its entanglements are part of that identity, part of what makes it the specific quantum object it is and not another. So when the encrypted copies came out still carrying the original's entanglements, still woven into the same web of connections the source had belonged to, it meant the copies were not merely surface imitations. They were faithful all the way down, preserving not just the state of the qubit in isolation, but its relationships, its place in the larger quantum world around it. The copies inherited not only what the original was, but how it was connected to everything else. For a scheme meant to duplicate an identity, that is about as complete a fidelity as you could ask for. I think it is worth sitting for a moment with how quietly astonishing this whole thing is, because the language of physics papers has a way of draining the wonder out of extraordinary events. Strip away the technical vocabulary and look at what actually occurred. Two people noticed that a 40-year-old rule everyone treated as an absolute wall had a shape more subtle than anyone had bothered to check. They found a way to make perfect copies of quantum information by hiding it inside noise, copies that respect the old rule because only one can ever be read. They proved it with mathematics rigorous enough to satisfy one of the toughest journals in science. And then they went to a real quantum machine, one of the most advanced ever built, and they made it happen in the physical world, with atoms and fields and currents, and it worked beautifully. A thing that was considered flatly impossible for 4 decades is now something you can do on a Tuesday afternoon on a computer in a lab provided you are clever about it. That is not a small event. That is the kind of thing that quietly rewrites a corner of what we thought was permanent. To appreciate why running this on real hardware is such an achievement, you have to understand just how hostile the physical world is to quantum states. The processors these experiments run on have to be chilled in elaborate refrigerators to temperatures barely a whisper above absolute zero, colder than the darkness between the stars, because the faintest warmth would jostle the qubits and scramble their delicate conditions. Even inside that profound cold, a qubit can typically hold its quantum state for only a tiny fraction of a second before the surrounding world creeps in and corrupts it, a problem physicists call decoherence. Every operation has to be performed within that fleeting window, quickly and precisely, before the fragile state dissolves back into ordinary noise. This is the environment in which the encrypted cloning scheme had to prove itself, a machine where quantum information is always seconds, or fractions of seconds, from falling apart, where imperfection is not an occasional visitor, but a constant pressing presence. That the scheme worked at all in such conditions is impressive. That it worked well and proved comfortable with the machine's imperfections is the part that turns a clever idea into a genuine tool. The detail about entanglement surviving the copying deserves a second look, because it speaks to how complete the duplication really is. When physicists say the encrypted copies remained entangled with the qubits the original had been linked to, they are saying something about fidelity that is easy to underrate. A quantum object is not fully described by its own isolated state. Part of what it is lies in its connections, the way it is woven together with other particles into a single shared system through entanglement. A copy that reproduced the qubit's private state but severed all its relationships would be a hollow imitation, a portrait that captured the face, but none of the ties to family and history that make a face belong to a particular life. The copies these researchers made did not do that. They preserved the entanglements, kept the qubit's place in the larger web of connections intact, so that each sealed duplicate was faithful not only in itself but in how it related to everything around it. For a scheme meant to copy an identity, that completeness is the whole point, and seeing it hold up on real, noisy hardware is what tells you the effect is solid rather than a fragile trick of the mathematics. And yet, precisely because this is a place where we care about the difference between what is true and what merely sounds exciting, I have to slow us down and ask a harder question, the question a careful scientist would ask before letting any of us get carried away. When you strip away the drama, when you look at what actually came out of that machine, is this really cloning at all? Did they truly copy a quantum state in the sense that word implies, or did they do something subtler that only wears the costume of cloning? Because there are respected physicists who look at this result and say, with good reason, that calling it copying is generous, that what really happened is more modest and more peculiar than the headline suggests. This is not a criticism that weakens the discovery. If anything, understanding the objection makes the achievement clearer and keeps us honest about exactly what was and was not accomplished. So before we follow this all the way out to its meaning for you and me, we owe it to the truth to ask the skeptic's question directly. Is it really cloning, and does the answer change what any of this means for the one and only you? Part 10. But is it really you? The objection comes from Mark Hillary, a physicist at the City University of New York who has spent his career working on exactly this kind of quantum information science, which means he is not a skeptic waving away something he does not understand. He knows the field intimately, and his question is a fair one. He points out that at the end of this whole procedure, only one qubit ever actually ends up in the original state. Only one copy is ever readable, ever usable, ever a genuine present duplicate. The others remain locked in noise, and if you can never open them, in what sense do they really count as copies at all? A copy you can never look at, never use, never distinguish from random static is a strange kind of copy. So Hillary asks, reasonably, whether it is right to call this cloning in the first place, when the thing cloning is supposed to give you, namely several usable duplicates existing at once, is exactly the thing you never get. I think it is important to hold this objection carefully rather than brushing past it, because it cuts right to what did and did not happen here. And getting that clear is the difference between understanding this discovery and being fooled by it. The headlines, including the framing that brought many of us to this story in the first place, tend to say that physicists shattered the no-cloning theorem, that one of the most unbreakable laws in quantum physics finally broke. And that framing, exciting as it is not quite true, and the truth is more interesting than the exaggeration. The no-cloning theorem did not break. Nobody found a mistake in it. Nobody disproved it. It stands today exactly as solid as it stood in 1982, a proven mathematical fact that has not developed a single crack. What Kempf and Yamaguchi did was not to break the rule, but to discover that the rule was more specific and therefore less restrictive than everyone had assumed. They did not knock down the wall. They found that the wall had always had a doorway in it, narrow and precise, that no one had noticed for 40 years. This distinction matters enormously, and I do not want to let the drama of the title paper over it, because on this channel, the honest version is always the more remarkable one. There is a world of difference between the claim that physicists proved you can copy quantum information after all, and the claim that physicists found a clever way to make sealed copies that respect the old prohibition perfectly. The first would be a revolution that overturns decades of settled science, and it would frankly be a little suspicious, the kind of too-good-to-be-true announcement that usually turns out to be a mistake. The second is what actually happened, and it is better precisely because it is true. The rule that only one clear copy can ever be read was not violated. It was upheld in a new and unexpected setting, by a scheme that seemed at first glance to defy it. What broke was not a law of physics. What broke was an assumption in our heads, the lazy shorthand that treated the theorem as forbidding more than it really did. That is a discovery about the limits of our own understanding, which is often the most valuable kind of discovery there is. Hillary, for all his precision about the terminology, is not dismissing the work. Far from it. He calls it a very nice result, and he points to something genuinely new that it accomplishes, something that sets it apart even from quantum teleportation. In ordinary teleportation, the state moves from one specific particle to one other specific particle, a fixed sender and a fixed receiver, and completing it requires that extra classical message and a correcting operation at the far end. This new scheme does something teleportation cannot. The quantum information can end up in any one of many different qubits, your choice of which sealed box to open, and remarkably, no classical message and no correcting step are required to make it work. That is a real and useful novelty, a new capability that did not exist before, and it is why serious physicists are paying attention even as they argue about what to call it. The debate over the word cloning is not a debate over whether the result is real or important. It is debate over how best to describe something that genuinely does not fit neatly into the old categories, because it is a new thing, and new things always strain the language we inherited from before they existed. So let me try to state, as honestly and cleanly as I can, exactly what was accomplished, stripped of both the hype and the dismissal. It is now possible to take an unknown quantum state and produce many perfect, sealed, encrypted copies of it, using noise as the lock and a one-time key as the seal. Every one of those copies is a faithful and complete imprint, preserving even the original's entanglements with the wider world. You can make as many as you like, without any loss of quality, and you can open exactly one, ever, because opening it consumes the only key. The no-cloning theorem remains true, because you never hold two readable copies at once. This is not the old rule broken, it is a new and richer picture in which the old rule turns out to permit far more than we realized. So long as it's one true prohibition, the ban on ever reading a second clear copy is honored. That is the accurate story. It is less like a law collapsing, and more like discovering a hidden room in a house you thought you had fully explored. There is a pattern in the history of physics worth knowing here, because it puts this whole episode in its proper light. Again and again, a result that gets announced as the breaking of some famous rule turns out, on closer inspection, to be something more careful and more interesting. The discovery that the rule was narrower than everyone had lazily assumed. The rule does not fall. Our understanding of its exact reach expands. This is not a disappointment. It is very often how real progress happens, not through the dramatic collapse of an old truth, but through a sharpening of it, a finding that the wall we thought ran in a straight line actually has a shape, with corners and gaps we had never bothered to map. The people who make these discoveries are rarely the ones shouting that everything we knew was wrong. They are usually the ones quietly insisting that we did not know quite as precisely as we thought we did, which is a humbler claim, and, in the long run, a far more powerful one. That is exactly the character of what happened here, and holding it clearly is what keeps us honest without dimming the wonder. Nobody caught the no-cloning theorem in an error. It is as true today as ever, and it will still be true 1,000 years from now. What changed is that we learned its true shape, learned that it forbids only the reading of a second clear copy, and never forbade the sealed copies at all. The distinction Hilary insists on, that only one qubit ever really ends up in the original state, is not a deflating footnote. It is the exact statement of what makes the whole thing consistent, the reason the workaround and the theorem can both be true at once. And once you hold that distinction properly, the result does not shrink. It settles into something sturdier than the headline, a genuine and permanent addition to what we understand about the limits of copying, arrived at, not by demolishing an old certainty, but by finally seeing all of its edges. The honest version asks a little more patience of us than the dramatic one, and it rewards that patience with something that will not fall apart on closer inspection, which is the only kind of wonder worth building on. And here is why, even after all that careful deflation, the result loses none of its force for the question we actually care about. You might think that once we admit only one copy is ever readable, the whole thing becomes a technicality, a clever bit of quantum bookkeeping with no bearing on anything as human as identity. But look at what the honest version actually says, and feel how it lands. It says that the universe is now willing to let 1,000 perfect copies of a quantum state exist at once. It draws only one line, and it draws that line in exactly the place that matters most. You can be copied endlessly. You cannot be read twice. The constraint is not on your duplication, it is on your presence, your awakeness, the singular fact of there being one clear you. Which means the deepest question this discovery raises is not really about qubits or encryption at all. It is about what it would be like to exist as 1,000 sealed copies, scattered and dormant, with only one of you ever permitted to open its eyes. That is not a technicality. That is one of the strangest situations any thinking being has ever been invited to imagine, and it is where we go for the final stretch of our journey tonight. Part 11. The backup you can never open. The practical uses the researchers imagine for this are, on their face, sober and technical, and I want to walk through them, because even the dry engineering version carries a strange emotional charge once you have followed us this far. The first application is redundancy, the quantum version of the thing you do every time you back up a photograph. Until now, quantum information could not be backed up at all, and that was a genuine obstacle to building quantum technologies that people could rely on. A single qubit holding precious quantum data was a single point of failure, and if it was disturbed or lost, the information was simply gone, with no spare anywhere. Encrypted cloning changes that. You could now store many sealed copies of your quantum data in many different places, a quantum equivalent of cloud storage, so that no single accident could erase it. The researchers even use the phrase encrypted quantum multi-cloud storage, which is a mouthful, but the idea underneath it is simple and human. It is the ability, at last, to keep a spare. The other uses follow the same shape. Quantum communication and quantum sensing could be made far more robust, because instead of sending a single fragile qubit across a noisy channel where any disturbance might destroy it, you could send a whole stream of encrypted copies, confident that the information would survive the journey even if many of the individual copies were battered along the way. And more ambitiously still, Kempf and Yamaguchi hope eventually to find ways of performing actual computations directly on the encrypted qubits, doing useful work on data that no one, not even the machine doing the work, can read. Picture a future quantum cloud service that could store your quantum information across many locations for safety, and also compute on it for you, all while the information itself stayed sealed and private the entire time, never once exposed, never once readable by the very service holding it. It is a vision of a kind of privacy so complete that even the keeper of your secrets could never learn them. But you and I did not come here tonight for cloud storage. We came for the question of the self, and this is where the technical picture and the human one fuse into something I find genuinely haunting. Because if you are, at the deepest level, a quantum pattern, then everything we just described applies to you. It becomes possible, at least in principle, to make 1,000 sealed copies of the pattern that is you, and store them in 1,000 vaults across 1,000 worlds. A backup of a person, the thing the no-cloning theorem seemed to forbid forever, turns out to be permitted after all with the one-iron condition attached. You can be backed up endlessly, but you can never be restored more than once, and you can never, ever read 2 of the backups at the same time. You're not a file, we said, and it is still true, but now the truth has grown teeth. You can be saved 1,000 times over and remain, always and only, restorable to a single waking self. Let me put you inside that future for a moment, because I think it is the strangest place this whole story leads. Imagine you stepped into such a machine years ago, and 1,000 encrypted copies of you were made and scattered across the galaxy, sealed, dormant, waiting. You never felt anything. Now imagine that on some distant world in a quiet vault, a technician finally turns a key. The static lifts from one copy, and you open your eyes. You're lying in an unfamiliar room on a planet you've never seen, and yet you remember everything. The machine, the decision, the life you led before, all of it seamless and whole and unmistakably yours. You sit up and you know with total certainty that you are you. But somewhere out there, in 999 other vaults, on 999 other worlds, the other copies lie sealed in their static, and now that you have woken, they never can. They were as perfect as you. They had as much claim to your name and your memories as you do. And the only thing that makes you the real one, the living one, is that yours was the key that turned. Choose a different vault, and a different copy would have woken, just as certain, just as convinced, and would have been just as fully you. The one who wakes is always the real one, and there is never more than one, and which one it is comes down to nothing but where somebody happened to turn a key. I find I cannot decide whether that is the loneliest idea I have ever encountered, or the most reassuring, and I have come to think it is somehow both at once, inseparably. It is lonely because it means that no matter how many copies of you might exist, you can never be joined by another waking you, never meet yourself, never share the burden of being you with a second self who understands completely. The singularity is total. Even in a universe stuffed with 1,000 sleeping versions of you, you would still wake and live and face everything, entirely alone in the specific way that only a single conscious self can be alone. And yet it is reassuring for exactly the same reason, because that same law means the you that is here, now, reading these words, is not a redundant instance, not one of a crowd, not a copy whose loss would hardly matter because another could always be opened. You are the one clear copy. Whatever else is uncertain, the universe has arranged things so that there is only ever one waking you, and it is you, and that has a weight and a preciousness that a mass-produced, freely duplicated self could never have. It is worth dwelling on how total the privacy of such a system would be, because it is a genuinely new thing under the sun. In every form of data storage we have ever built, the keeper of the data can, in principle, read it. Your files sit on someone else's machine, and while good encryption can make them very hard to read, the fundamental arrangement is always one where the information is, at some level, exposed to whoever holds it. What encrypted cloning points toward is something different in kind, a way of storing quantum information across many locations where the very things holding your data cannot see it, cannot read it, cannot ever learn what they are keeping, because the information lives sealed inside its noise, and only your single key could ever lift the veil, and even then only once, in one place. A vault that does not know what it guards, a cloud that holds your secrets, and is itself forever blind to them. If the researchers succeed in their more ambitious hope of computing directly on the sealed data, then you could even have work done on your information by a machine that never once glimpses it. It is a kind of trust that would not require trust at all, because betrayal would be physically impossible. But turn that engineering marvel back toward the self one more time, and the wonder acquires a shadow. If you could truly be stored this way, scattered in sealed copies across many worlds, then in a strange sense you would achieve a kind of immortality, a permanence that no fragile single body could ever offer, your pattern preserved against every accident, waiting in 1,000 vaults for a key to turn, and yet the permanence would be of the loneliest kind. None of those stored selves would experience anything as they waited. They would not dream, would not think, would not know they existed, because to be read is to be one, and only one can ever be read. You would be everywhere and nowhere, preserved and absent, 1,000 times saved, and never once, in all those vaults, more than a single waking soul. The dream of backing yourself up, chased so hopefully by so many, turns out to lead here, to a room where you are infinitely safe and still, in the only way that matters, exactly as alone and exactly as singular as you have always been. The universe will let you keep as many copies as you like. It will simply never let more than one of them be you. There is one more turn to take before we close, and it brings us all the way back to where we began, to the person standing on the teleporter pad, and to the sleepless question that started this whole journey. Because now we have the physics in hand, and it does something I did not expect when we set out. It does not answer the old fear exactly, but it reframes it, and in reframing it, it offers something that feels almost like peace. We spent the first half of tonight learning why the teleporter might be a machine that quietly ends you, why the original never survives the trip, why you're not a file that can be safely saved. And we spent the second half learning that the universe, for all its new cleverness about copies, still guards the one thing that matters most about you more jealously than we ever realized. So in the final part, I want to gather all of it together, the rule and the workaround, the terror and the comfort, and ask what it truly means to live as the one clear copy the universe will ever allow you to be. Part 12. One clear copy. So let us go back to the pad one last time, to that warm and humming room where a person stands deciding whether to step forward into the light. When we began, that scene was pure dread, because we understood that the original never survives the trip, that if the machine works by reading you out and rebuilding you elsewhere, then the you who walks in has to end so that the copy can begin. Nothing we have learned since has erased that. The teleporter, taken seriously, is still a machine that would move you by ending you, and the person who steps off on the far side, whole and smiling and certain, would still have no way to know whether they are the continuation of the traveller or a flawless newcomer who has inherited a life. The physics does not rescue us from that. If anything, it has shown us the rule is even more absolute than we feared. There can only ever be one clear copy, and to move it is to remove it, and no cleverness with encryption changes the fact that the pattern, which is you, cannot be in two waking places at once. And yet something has shifted in how that lands, and I have been trying all night to name it. It is this. The same law that makes the teleporter frightening is the law that makes you real. Follow it carefully. The universe forbids a second readable you not out of cruelty, but because that is what it means for a thing to be genuinely singular, genuinely itself, rather than one arbitrary instance among endless interchangeable copies. When we imagined the 1,000 sealed backups scattered across the galaxy, the thing that made the loneliness bearable, even beautiful, was precisely the rule that only one could ever wake. If 100 of you could be awake at once, freely copied and pasted like a photograph, then there would be nothing special about any particular one, including the one you are. Your being here would be cheap, redundant, replaceable. It is the impossibility of the second waking copy that makes this one, the one reading these words right now, matter the way it does. I keep returning to that sentence of Kempf's, because it has quietly become the whole point. There only ever can be one clear copy of the quantum information, and it is mandated by a law of nature. He was describing a laboratory result about qubits and encryption keys. But if you are the kind of pattern that lives in the quantum world, then he was also, without meaning to, describing you. There is only ever one clear copy of you, and it is not one because technology has not caught up, and not one because we have not tried hard enough to make more. It is one because the deepest rules of reality reach down and hold it so. You are protected from duplication by the same law that protects a quantum secret from a spy, guarded at the level of physics itself, sealed against ever being turned into a crowd. The thing you might have feared was a limitation. The fact that you can never be backed up, never be copied to safety, turns out to be indistinguishable from the thing that makes you unrepeatable. The curse and the gift are written in the same line of the same law, and you cannot have one without the other. There is a particular comfort in this that I did not expect to find when I started losing sleep over teleporters, and I want to offer it to you plainly, because I think it is real, and not merely a pretty way of dodging the fear. Whatever happens, whatever machines we build or never build, whatever the future holds for copies and clones and quantum clouds, the you that exists tonight is the one clear copy the universe will ever permit. Not a draft, not a spare, not one of many. The single waking instance of a pattern that has never existed before in the history of everything, and, by a law as firm as any in physics, can never exist again once it is gone. That is not a small thing to be. In a cosmos where light itself obeys a strict and absolute limit, where the largest structures and the tiniest particles all bend to unbreakable rules, one of those rules has quietly been working the entire time to guarantee that there is exactly one of you, here, now, awake, irreplaceable. You did not have to earn it, and you cannot lose it to a copy. It was reserved for you before you drew a breath. The physicists, of course, are not thinking about any of this. They are thinking about encrypted cloud storage and robust communication, and the tantalizing possibility of computing on data no one can read, and those things may well reshape technology in the years to come, and I hope they do, because it would be a strange and wonderful thing to live in a world where quantum information can finally be kept safe. But underneath their careful, practical work sits this other discovery, the one they did not set out to make, the one that belongs as much to philosophy as to physics. They went looking for a way to protect fragile quantum signals from noise, and they came back having shown, in a real machine, that the universe will let you be copied 1,000 times, and still insists, absolutely, on there being only one of you awake to know it. They found the exact shape of your singularity, and they found that it holds even against infinite copies. That is a stranger and more intimate result than any storage scheme, and I suspect it will outlast all the applications quietly, the way the best ideas do. Think about the company this rule keeps, because it tells you how far down it runs. The universe is governed by a small handful of absolute limits, and most of them we have learned to live with, even to find beautiful. Nothing can outrun light, and because of that, cause always comes before effect, and the sky you see is a record of the past, and reality is spared the paradoxes that faster signals would bring. Energy is never created or destroyed, only moved and transformed, and so the cosmos keeps a perfect ledger through all its violence and change. These limits do not feel like prisons once you understand them. They feel like the conditions that make an ordered world possible at all, the firm walls inside which everything meaningful can happen. And now we can add another to that short list of absolutes, one that has been quietly enforced since long before there were minds to notice it. There can only ever be one clear copy of a quantum state, one readable instance of any truly quantum thing, and if you are such a thing, then there can only ever be one clear, waking you. It sits alongside the speed of light, and the conservation of energy as a rule the universe simply does not break. I find it strangely moving that this particular limit, of all of them, should be the one that guards something as intimate as a self. The others govern light and energy and the grand machinery of the cosmos, distant and impersonal for all their importance. This one reaches all the way in, past the galaxies and the stars and the atoms, down to the pattern that is a person, and it draws its single unbreakable line right there, around the fact of your being one. Of all the things the universe could have left unprotected, it chose to enforce, with the full weight of physical law, that you cannot be duplicated into a crowd, cannot be diluted into one instance among many, cannot be made less singular by any machine however clever. The rule that first looked like a locked door barring you from safety turns out to be the same rule that stands watch over your uniqueness, and you cannot pry the two apart because they were never two things. They were always one law, wearing a frightening face and a tender one at the same time, and which face you see depends only on whether you're looking at what it takes from you or at what it will never let anyone take away. So the next time you cannot sleep, and the old question comes to find you in the dark, whether the person who steps out of the teleporter is really you, I hope you will remember what the universe has to say about it. The answer is not the comfortable one, and it is not the terrifying one. The answer is that there can only ever be one clear copy of you, that this is mandated by a law as old and as firm as the constancy of light, and that the one clear copy is the one that is here, breathing slowly, listening to this, alive in a single unrepeatable moment that will never come again and never be duplicated. Everything that made teleportation frightening is the same thing that makes your existence extraordinary. You cannot be saved to a file. You cannot be copied to safety. You cannot be met by a second waking self who shares your burden. And for exactly those reasons, you are the one and only place in all of reality where this particular pattern of a universe wakes up and knows that it is here. There has never been another. There never can be. Rest easy in that. Of all the things the cosmos guards so fiercely that no machine will ever undo them, one of them, it turns out, is you.